we have Poiseuille's equation and Bernoulli's equation. Bernoulli's equation states that the velocity and pressure goes in different directions. Velocity increases as pressure decreases. For example, we have this blood vessel. If now we reduce it like this, the pressure, the forward pressure, let's say we have this, and then now passes to this. So we are putting a stenosis here. The pressure forward is decreasing, and if we decrease the pressure, the velocity will increase. And for that, capillaries have greater velocity than the velocity, for example, of the aorta. That's one issue. So when we put a stenosis or a resistance in a blood vessel, we are decreasing the pressure forward and increasing the pressure backwards. This increases the gradient, the delta P. So when we put a stenosis, yes, we think about that there is less perfusion because of the resistance, but actually the flux will be increased because there is the increase in the gradient. We have flux or Q, but I put flux like this, like the derivative. This is dV, the volume in dt. This was velocity like this. The volume in dt is the same as fluxion in Newton's symbology. This is Leibniz's symbology. Alright, so this is equal to the change in pressure divided by the resistance. So because here the change in pressure increases, the flux increases. The reason for which there is no increased perfusion is because the resistance increases. Now, we know that the resistance is equal to, by Poiseuille's law, is the viscosity times the length, h times this, divided by p r to the fourth power. So we know that if the radius increases by 2, the resistance decreases with the fourth power, so decreases 16 times. If the radius decreases twice, the resistance increases 16 times, and so this is very intuitive. With 3, the radius increases 3 times, the resistance decreases 81 times. And if the radius decreases 3 times, the resistance increases 81 times. Now, if we substitute this here, we have that flux is equal to change in pressure divided by p r to the fourth power. This 8 times the viscosity times the length divided by p r to the fourth power. We send this to the other side, and we have change in pressure times 8 times the viscosity times the longitude divided by p r to the fourth power. So now we have that flux is inversely proportional to the radius. If the radius decreases 4 times, if the radius decreases 2 times, this goes to this side, so it's pi r to the fourth power divided by 8 times the viscosity times the length. And now we have that flux is proportional to the fourth power of the radius, as we hoped here, it was expected here. So again, if we increase the radius twice, the flux increases 16 times. If we decrease the radius twice, the flux decreases 16 times. And this is what every cardiologist think once they understand that the radius is not directly proportional to the flux. That is, the flux is proportional to the fourth power of the radius. Once that cardiologists understand this, now they work like this. Actually, the flux is not proportional to the fourth power of the radius. This is due to, remember here that we said that if we put a resistance, this resistance is we're decreasing this radius, the area of transversal section, of cross section, and so we're increasing the delta P. The delta P is increasing, and when we increase the delta P, we increase flux. So look this. Delta P in the pressure is equal to force over area. So here we have volume is equal, flux, volume dV in dt is equal to force over area times P r to the fourth power times 8 viscosity longitude. We can multiply by a convenient one. We can multiply everything by pi. And so now we have force divided by area times, this is pi square r to the fourth power divided by 8 viscosity length. This is the same as PR square is area. So area squared would be square pi r to the fourth power. So this we can put it as force times square area divided by area times 8 viscosity length. So we can cancel this. We return the area to PR squared, and we have the flux is equal to force times area is pi r squared divided by 8 times the viscosity times the length. And now we have that the flux is proportional to the square of the radius. That is, if the radius decreases twice, the flux decreases 4 times, not 16 times. This is due to this. When the pressure changes because of the radius, also the flux is going to change. That is, pressure is equal to force divided by area, and this is force divided by pi r squared. So the pressure is inversely proportional to the square of the radius. If the radius increases twice, the pressure decreases 4 times. So we have here we have that, or yes, well, we can put it as volume as flux is equal to the where this here we can use this one, and here we would put a force divided by pi r squared times pi times r to the fourth power divided by 8 viscosity length. Again, here we cancel these pi's, and this goes to square, and we have the same thing. Oh, sorry, here I forgot to put a p here, and so here there is no pi. And the important issue is that now the flux is dependent on the square of the radius, because if the radius decreases twice, the pressure increases 4 times. So pressure goes up 4 times, and here the radius is decreasing 16 times. So 4 divided by 6 is 4, that is r squared. So because pressure also depends on the radius, when the radius changes, pressure changes, and pressure changes are reflected also in the flux. So the flux depends on the square of the radius and not in the fourth power of the radius.